Hello, and welcome to the instructional video for your at-home lab on forces. In this lab, we're going to use a kitchen scale and an object and a tray like I have here. This lab doesn't have very much analysis. It mostly just focuses on working with a couple of simple pieces of equipment and making some interesting observations. Okay? So in other words, you won't have to use any software on your computer. All right. So the first thing I'm going to do is just turn on my scale, make sure it's set to grams. Okay? Then I'm going to place my object on the scale and see what the mass of that object is. In this case, it's 126 grams. Okay? So then for part one of this lab, for experiment one or procedure one, you're going to quickly raise or lower the tray with the scale on it, with the weight on the scale. So for example, I could quickly raise it up. Let me do that so you can maybe see it in frame. And you can see on the way down, one more time. But you can see on the way down, the numbers change. On the way up, the numbers change. So in what direction do they change on the way up and on the way down? Well, the measured mass of the scale, the weight reading of the scale is increasing when I quickly raise the tray. When I quickly lower the tray, as you saw, the weight reading decreased. So what you're going to do is you're going to look at a video and look at the frames, basically just slide through it, and you don't have to film at a high frame rate. The frame rate that I'm using for this video would be sufficient. For example, you could have paused this video and kind of just moved through and found one part of the video and seen a number, a mass reading in grams from the scale that is measuring weight. And when you see that number, then you're going to be able to calculate the instantaneous acceleration at that point in time, or at least an approximation of it. Okay? So that's what you're going to be doing. You're just going to be making a calculation of acceleration based on the weight reading that is coming from the scale. You're also going to have to draw a free body diagram that kind of justifies how you made that connection. I also included the equation that relates to relating measured weight to gravitational force to acceleration. Okay, in this case, the acceleration of the tray, which of course is also the acceleration of the scale, and the this is my object, which is all going together. Okay, so that's all you're going to do for procedure one. Now let me show you what is going to happen for procedure two. Okay, so we're back to our tray. It's at rest. And what I'm going to do is I'm going to tilt the tray up. And notice what happens. What's happening to the number, the weight reading, measured in units of mass, measured in grams on the scale. It decreased, right? It continued to decrease until it finally got to a value where the object slid off. Well, you want to find the moment right before it slid. So let's do this one more time. Okay, so it's decreasing. 125, 124, 123, 122, 121. All right, and it slid off. And then at that angle that I was at, notice that there is a reading of -3 grams. Okay, so that means that the scale was inaccurate by 3 grams. Because the scale's tipped, then it doesn't work properly when tipped. So all you're going to do is take into account that inaccuracy. Because see how the inaccuracy is really a function of the angle of tilt? And so you just need to take account of what was that spurious mass once the object slid off. Now notice that it is a bit different. You can repeat this process to find a number that shows up each time. Okay, let's do it again. Look at this time, it was more like 118, okay? And the first time it may have been 117, if I recall correctly. So the idea is that you want to find kind of the value that you think is most reliable. Mostly I'm just concerned with the process and the free body diagram that accompanies it and kind of thinking about, how forces work. That actual accuracy, well, that's going to, you'll be able to think about that when you kind of compare it to the material that you're using and you look it up based on a table of common friction coefficients for that material. Because the actual calculation you're going to make is going to be to calculate the friction coefficient, which is a dimensionless value that relates how easy something is to slide, how in between two surfaces. In this case, I kind of have a biological surface is actually a piece of coral, and that complicates things, right? If you might want to use something that's a bit more uniform, mine obviously is giving some messy results, like, say just like a plain block of plastic or a block of wood, something that is a bit more predictable. That said, friction is messy, and you're going to get different results, okay, if you repeat the trial. But if you repeat it enough, you may see a number that is coming up a lot, and then you can kind of either take an average or just find, that maybe the mode, right, the number that occurs the most in terms of the final weight before the object slid off. So you're going to do that. You're going to do two different objects. I'm just showing one, but you'd have to choose a different object in addition to the first object you used. And I mentioned you also need to measure the actual height when the object slid off. So for example, if it slid off at this height, here, let's extend. I'd have to measure how high off the table, something like that, okay, but more carefully, obviously, how high off the table the corner of the tray is, and then measure the distance from wherever I measure the height. So say if I measure the height to this point, this corner, then I'd have to measure the distance along, like the hypotenuse, along the tray or flat surface until it makes contact with the ground, okay? So those two measurements will allow you to calculate the angle of the tilt, right? So the actual angle that the tray or board is tilted at. And that means that you would then have an independent way to calculate the friction coefficient using geometry rather than just using measured weight on a scale, okay? And again, you would just measure the hypotenuse and one leg of the triangle, which would allow you to calculate the angle, okay? All right, but then you are asked for percent error between those two methods. The method of finding the angle with the measurements and your measuring tape, and finding the angle, and then finally also finding the friction coefficient by the measured weight, which is also known as the normal force. Okay, so that's it for the directional video. Again, because there's no extra analysis, I just wanted to show what the actual procedure would look like, in terms of tilting the scale and quickly raising and lowering it. All right, well, thank you so much for watching. I hope the lab goes well, and send me any questions that you have.